Okay, so I'm going to go through Ohm's law, basic Ohm's law, which I think maybe you guys have seen before in science, but if not, it's worth going through. And then I have series circuits and parallel circuits planned. I think doing all three is going to be too much, and so I'm going to do Ohm's law and series circuit today, and then next time I'll do parallel circuits. All right, so here is Ohm's law, the relationship between the voltage, the resistance, and the current. Okay. I'm not going to get into what all those things mean so much. This is mostly for the math. How do you use Ohm's law? That's what this little video is for. So I like this little graphic organizer to help you figure out how to use the formula. Except that it's kind of saying, hey, you don't have to worry about the algebra. Here's what the algebra will look like. So if you're thinking algebra, which hopefully nobody in here does, this little graphic organizer here helps you. So let's say you want to know how to figure out the current. The current, I is the current. It's measured in amps. So C for current, no, it's I. What's the unit of measurement? It's amperes. So capital A. It doesn't make a lot of sense. Current, the variable you always use is I. So this is an I, not a 1. This is an I, not a 1 over here. And then the unit of measurement is in amps. Okay? And so you use V over R. And so you just cover up the thing you want to. You've got this triangle here, V and then I and then R. Cover up what you're trying to figure out, then V over R is the formula. Cover up the R, you get V over I. Cover the V, you get I times R. Alright? So here's Ohm's law. I equals V over R, and then they have this little graphic organizer to help you solve for the variable you want to figure out, just in case you don't feel like doing algebra, which I can understand. I don't feel like doing algebra sometimes too. Alright? So the other thing that, the thing that can potentially be an issue, other than having to do algebra, is make sure you don't mess up the prefixes. So we have kiloohms and milliamps in different examples. It is more succinct to use the SI prefixes like we have learned to do. However, you do not want to do math with them, really. So you got to convert back. And so really that activity that we did already is one of the most important ones, because you kind of got to be able to convert back and forth pretty quickly and easily. So I'm going to pause it and get these three problems separated a little bit, because this is a ridiculous mess. Here we have a situation where you have a voltage pushing. It's kind of pushing is kind of the metaphor you can use. The current through a section of a circuit. So this is just a section of a circuit. There's a whole bunch of stuff going on potentially. And it has this resistance of 1,000 ohms or 1 kiloohms. So that's actually the first thing you got to figure out, or one of the first things after you figure out that I'm going to use this version of Ohm's law, because we're finding current, only unknown here. So you're going to go I equals 9 volts voltage over 1,000 amp. Wrong thing. 1,000 ohms. And then, actually, I usually don't put the units of measurement in mid-problem. So let me just get rid of that sucker. Okay, it's 9 volts over 1,000 ohms, but mid-problem I never write the units. Well, obviously I do sometimes, because I just did. But here, so you just divide it. Use your calculator and you got, alright, 0.009 amps. Okay, now at the end of the course exam in May, on any sort of quiz or anything I give you, I don't want to see this answer. You have to annoyingly convert back to SI prefix again. So you switch to engineering notation, and so this is 9 times 10 to the negative 3, right? Boom, boom, boom. So 9 times 10 to the negative 3, 10 to the negative 3 goes with milli. So this is 9 milliamps. So you'd feel that, I guess, but it probably would not kill you, which is good. All right. So there you go, Ohm's law. So let's do this one. So here we have. Well, what's the thing missing? I don't know. Okay, I just realized I forgot to change the problem for the third problem, so oops. So I did that really quickly. Well, it wasn't that quick. I just paused the recording. But anyway, yeah, here's the third problem. So this problem, we're looking for R. No, we're not looking for R. We're looking for V. Jesus, screwed that up too. Boom. All right. V equals 5 volts. It's a little confusing maybe since the variable and the unit of measurement is the same. But anyway, back to this one. We have 220 ohms and 10 milliamps. So we have, going up here, we have V. If you cover up V, we have I times R. So we have V. This is actually how I learned Ohm's law. It's just with this one, and it was in college, so they didn't really, they weren't nice to you. They didn't say, hey, here's a little thing to make you not have to do algebra. You got to do the algebra in college, everybody. So there you go. But here, we're nice to you, you don't. So V equals IR, we have, hold on, technical difficulties we have. All right, I is 10 milliamps. So, ooh, I got to convert, and I'll do it quickly here. I'll do it in my head. So I is 10 milliamps and times 220. Okay. So V equals IR, and it's 10 is, or right here, 0.010 is 10 milliamps times 220, and so you get that equals 220 times 0.01, 22, nope, 2.2, excuse me, volts. Okay, you do 2200, yeah, there you go. Not 2200, what am I talking about? 220. It's getting late, so I'm starting to be stupid. So there you go. 2.2 volts is the answer there, and so you don't have to convert back because it's already in nice little SI notation. You don't have to move the decimal point at all. So here, V and I is what's given. So you could do algebra from this one and go figure out that V over I is what you need. R equals V over I, or you can just use this thing here and recognize R equals V over I with this little graphic organizer here. Alright. I probably shouldn't be pushing this little graphic organizer. I could force you, you guys should be able to do the math. Alright. And then so we use, this is equal to 5 over 0.015, and that is equal to 333.3, what are we looking for? Resistance, and so it's going to be in ohms. Okay, so whenever you're doing math with Ohm's law, your units of measurement, you have to remember to be in ohms, amps, and volts. Okay, if you don't, then your decimal point, basically your decimal point is going to be in the wrong spot. All right, and then do we need to switch this to any sort of special notation? No, we're good to go. 333 1/3 ohms is what that would work out to be. Okay, there you go. Ohm's law. So series circuits. This is, check it out. This is a standard series circuit. The total voltage is 12, and we have 1, 2, 3 resistors. So how do you do the analysis on this guy? Well, basically, the problems in the exercise you'll see, you'll be told what the resistances are. And what you have to figure out is all this stuff over here. And this is basically the order in which you have to figure out. You got to figure out the total resistance, and you can use that to find the total current, and then you can find the 3 individual currents, or excuse me, voltages that are measured across each resistor. Okay? So the total resistance. The total resistance, so if this was 1 resistor, what would these 3 resistors be equivalent to? That's the total resistance. In a series circuit, that's easy. It's just, hey, add them up. Add up the 3 resistors. So to find RT in a series circuit, you just take the 3 and you add them up. So it's 100 plus 1200. Wait, where did I get 1200? Well, right here. That's 1.2 kilo ohms. You don't do 100 plus 1.2 plus 470. It's got to be in ohms. All the math you do has got to be in volts or ohms or amps. You can't use milliamps. You can't use kilo ohms. You can, but you got to be real careful. You got to be pretty good at it and pay attention to everything a lot more. If you're just in the regular ohms, regular amps, regular volts, then you're good to go. And then plus 470 And then so this is 1770 ohms, okay? Or 1.77 kilo ohms. And that's how I would write the answer, but I'm going to use this number, so I'm just going to chill, and this video is already going a little long. So then we find IT, and that's just the Ohm's law. So the total current in a series circuit, there's only one path for the current to go, so it's always the same no matter where you measure it. That is not the case here in a parallel circuit. You actually end up with a total current, and then 1, 2, 3 currents within each path. But anyway, we have one total current, and it's I equals VT over RT. So that's why you have to find RT first, because it goes in the next formula. So VT over RT is that, and I'm not going to lie, I'm going to pause and use Mr. Calculator. And we get, I just looked and I lost it. What is it? We get 6.78 milliamps. So we get, let me scroll down a little bit. We get 0.00678 amps, or I will write it out on a we move it over 1, 2, 3 places. So we got 6.78 milliamps. Okay, so there you go. And then what we can do is we can, now that we have the total current, that is the total current, and it's everywhere, no matter where. So if it's going here near R1, near R2, near R3, it's all the same thing. And so what's up? To find V1, V2, and V3, okay, to find these guys, we just use Ohm's law again. So in this case, but now what we have is well, we're looking for V, so it's IR. So we have I is going to be the same for all of them. In fact, I'm going to be super lazy. Watch this. No, I don't want to use that one. Darn it. I want to use this. Alright, maybe. Oh, check that out. That was super loud. And then clone. Boom, boom. I times R. Same thing. It's the same IT. Kirchhoff's laws, that's the other important laws, say that voltage adds up in a series circuit, but current stays the same. And it's basically vice versa. Current adds up, the three currents that are on these three branches add up, and the voltage stays the same. So V1, V2 is I times R, because remember, IR. V equals IR. Where'd it go? V equals IR. So I times R, I times R times R. Now where are these R's? Well, they're right here. R1 is 100. So times 100. And then 1200. Ooh, that's not good. 1200. And then 470. And it would be good practice for you to, and then it's all over but the singing here. You multiply, 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 you get three answers, but guess what? This plus this plus this, that's going to add up to that. Alright? You'll get three real small, not that, what am I talking about? Oh my goodness, it's going to add up to, so this plus this plus this. I'm already thinking parallel circuits. Well, here you go, the 12 volts. 12 volts is the total voltage. So these three should add up to 12. And in fact, it would probably be a good idea for you guys to figure that out. Alright, so there you go. I'm about out of time. That was longer than I wanted it to be, but there you go. That should help you with a pretty good chunk of the next activity, that activity some of you had actually already started. But there you go.